Welcome, everyone. My desk is like a flea market bazaar. There's all sorts of things here. We're gonna experiment. We'll see how these things work. Originally, I wanted to make an electrostatic motor, but I've made a bunch of other things too. I wanted to show you the electrostatic motor because it's a type of motor, a high voltage motor, but it also has some theory and history behind it. Let's start with its history. Around 1750, Andrew Gordon and Benjamin Franklin were experimenting, and that's when they invented the electrostatic motor. Yes, you heard right, Franklin, who's on the $100 bill. So the electrostatic motor is linked to him and Andrew Gordon. It's basically all about charges migrating, and these charges are what will move the motor. In the following experiments, there'll be another very important thing, namely the point effect, or otherwise known as the corona effect. This here is a nail in my hand, and this is a printed circuit board with both sides coated in copper sheeting. If I connect this to a positive voltage and this to a negative voltage, and since there's air between them, what will happen is that a very high field strength develops here at the tip of the nail, and basically this high positive voltage we apply to the nail strips the electron from the air molecules, making them positively charged. Then the positively charged molecule starts moving toward the ground plate, toward the 0 point, and becomes neutral there.
For all of my experiments, or at least almost all of them, I'll be using this high voltage 20 kilovolt transformer. I made a motor like this, an electrostatic motor. Here are the blades in the drawing. I only drew two of them because I'm not the best at drawing, but in reality, I placed four. Here are three, and the fourth one is down there. This here will be the ion thruster. Here's the cylinder I mentioned, and here's a little tip, a partial tip. And at these points, I hope you can see, very thin wires are connected. This will be, so to speak, the lake on which this ion thruster will float. I made two types of it. This one is not even a gram, and that one over there weighs about 2 grams. I'll show you how it works as well. I think it almost takes off, but in the end it won't fly. At least I'd be really surprised if it did. And we'll fire up my Tesla coil too. I bought this one ready-made. It wasn't exactly cheap. It works, so we'll use this to ionize the air as well. This one, on the other hand, produces 20,000 volts. That's a big difference. But there's also a big difference in how dangerous they are. This one produces direct current, which is extremely dangerous. The Tesla coil operates at a frequency of about 100 kilohertz, and if a spark hits my finger, at most I just feel a burning sensation, but it's completely harmless. The electrostatic motor is an extremely simple device. At least the one I'm about to show you definitely is. You need a plastic cup for it. I tried using paper cups too, since all sorts of regulations have been introduced to reduce plastic waste, but it didn't work with a paper cup. I shared that story about the regulations because I had to search high and low to find a plastic cup, and this only works with a plastic cup. So if you buy one of those paper cups at the supermarket, unfortunately, it won't work with a paper cup. The likely reason is that the paper material of the cup conducts electricity to some extent, and because of that, this experiment just didn't work for me. Let me show you up close what this little electrostatic motor looks like. So the plastic cup, I placed several thin strips of aluminum foil on the outer surface, the outer shell, of the plastic cup. On top, there's a tiny little glass bearing. I'll show you in a moment how you can make one just like this. It's made from a light bulb. I cut off the top of a small car bulb, and that little spike in the middle is a 1 millimeter diameter drill bit, which is what allows the whole structure to spin around. As you can see, it rocks gently back and forth very easily, and it moves easily, and there are two electrodes. As I mentioned in my explanation about the point effect, maybe you can see it best like this. One electrode is attached here, and I couldn't resist making this little triangle, so there would be a small point, an aluminum triangle. And there's another one just like it on the other side, as you can see here. A green wire comes off of it, and a white wire as well. The white wire will go to the negative terminal of the generator, to the negative terminal, and the green wire to the positive terminal. So I'll get everything properly set up right now. Let's see exactly how this electrostatic motor is going to work. You simply have to connect one of the wires to one terminal of the 20 kilovolt generator. I'm going to use this small metal clip for that purpose, and the other wire to the other terminal, just like this right here. The clip didn't hold as expected, but I'll fix that immediately. Now, in this live demonstration, I'm going to turn on the generator. This specific generator is powered by this rechargeable lithium ion battery pack. Let's take a look and see exactly what happens. As you can see, it spins around and around very quickly. Let me show you this up close so you can see the detail. None of the tips touch the surface of the glass, neither the positive nor the negative. Basically, what I described is happening. So, what's happening is that this positive tip here and this positive tip deliver positive charges to the surface. Then it turns to the other side, and on this side, the negative pole neutralizes it. And so it keeps going around and around. It's also called a capacitor motor, not just an electrostatic motor. I've already turned off the generator, but you can see how good the bearings are on this thing. Even though it caught a bit just now, it keeps spinning for quite a while without any power. I'll show you how to build something like this. This kind of motor has very little torque. You have to make it very lightweight. Otherwise, if there's too much friction, it'll kill it. The rock and roll, and it won't spin. I put a skewer on this plastic sheet, and there's a 1 millimeter drill bit at the end. Any metal rod would have worked. This is just what I had on hand. And here are the two tips I made from aluminum foil. Here's one, and here's the other. Both tips are connected to the wires, one to the positive and one to the negative. First, you'll see there's a small hole. You have to punch a hole in the cup, and then I cut off the bulb of a light with a metal file. This specific bulb gave out very quickly. It's the kind they typically use for dashboard lighting in cars. And after it broke, I took out the filament and the socket part and securely attached it into place with two-component epoxy resin. If you don't have a 20 kilovolt power supply, like I don't, but you find a drain pipe at home, a PVC pipe, then grab the PVC pipe with a t-shirt like this so your hand doesn't touch the pipe directly, or find a pair of tights, a pair you don't use anymore. You can try rubbing the PVC pipe here, and if you bring it close to this little cup, you can see that you can move it with the pipe. If you're really skilled, you can even make it spin. So basically, the static effect works here too. You can see that it can start moving around in circles. I intentionally bent the tips out now. Obviously, not much charge remains on this pipe, but you can see that even this small amount of charge is enough to move this little cup. You can easily play with the cup at home, too. It's completely safe. The cup is totally harmless, so you can easily try this at home as well. I poured some water into this small plastic cap, and this is exactly what the ion engine structure looks like. I'll show it to you from every single angle. It's still a bit wet underneath because I just tested to see if it works, but I put 3 injection syringes on the bottom. So this'll look not like a catamaran, but a trimaran, meaning it has 3 bodies. These will keep the whole thing afloat on the water. At least that's the idea. So friction should be minimal. Or actually, I'm not even sure what to call it. Let's just say resistance from the medium. And here is an aluminum ring, and here there's a tip made from copper wire, and to the ring, this thin wire is attached. So one wire connects to the tip through this small wire segment, or rather through the thin wire segment, and there's another wire as well, which you can see here. The other wire is attached to this aluminum cylinder. I'm going to place this whole thing on the water and then connect the 2 wires to the 20 kilovolt power supply. I won't say it's completely safe, especially considering there's water involved. I'm turning on the power supply now. It very clearly swam across to the other side. I didn't even stop it, even though this wire is pulling it back a bit, so now it's come back here again. Let's watch it one more time. It swam across once again. I'll try to show it to you up close, so maybe you can see the tiny sparks in the middle. Honestly, I don't know what you'll be able to see from this. Try to focus on this part, and logically, the little raft will move in this direction. I'm turning on the power supply now, and it started. There were a couple of other sparks too, And this wire here is a bit flexible, so it tries to pull the little raft back. So that's how it works. It's a very simple little device. So this little raft works with ion propulsion and can smoothly travel from one shore to the other. Anyone who has seen a Tesla coil, or at least a video about it, knows very well that the Tesla coil also generates high voltage. Then here too, there will be an arc discharge, basically into thin air. Let me show you this. This ion thruster won't work with it, and the reason it won't work is because here we have alternating voltage, while this only works with direct voltage. But now let's check if that's really the case, as I claim. This comes from a charger adapter. It provides 18 volts. Let me show you what happened. Here you can see that at the end of the wire, yes, a nice little spark just formed right there, exactly like this. And this is what provides the necessary voltage. This high voltage comes from the Tesla coil, and now I'm going to connect this directly to the ion thruster, right into this part here. We'll see if the ion thruster, when powered by the Tesla coil, can actually cross this little pond or not. And I connected this specific part to that orange wire where you saw the arc earlier. Now I'm plugging in the device, and here too, the arc appeared, right here. You can probably see it quite clearly there at the end of the wire. Well, maybe this is the best way to see it. But there's no extra power, so the whole thing doesn't move at all. Someone might say that this whole raft is now very, very heavy indeed, and quite difficult to move, and the little coil can't provide as much energy as the other one. That's true. In theory, though, this should move. I've done this kind of experiment before. So I'm going to remove this cylinder, the aluminum cylinder, so that only the arc is there, and we'll see if the raft moves. I turned it on, the arc appeared again, though now the arc is a bit shorter than before. I'll show you. I don't know from which angle it can be seen best. Maybe like this. There's a nice little arc there, but the raft isn't moving. I have to admit honestly that I'm a bit uncertain here. I've done experiments before where, in this state, it did get the little boats moving forward, but this time it didn't move the raft, so it's probably an energy issue. Here are my two little electrostatic airplanes. I did everything I could to make them fly, but I still couldn't get it to work. Let me show you their exact weight. It's actually very instructive. It's completely zeroed out now, and I'll show you the display up close in just a moment. This is one of the small devices, and I'm putting it on the scale right now. And now I'm showing its weight, its total mass. It's about 1 gram. I hope it shines a little like this. Maybe it doesn't glare quite as much this way. This specific device is exactly 1 gram. It's pretty light. Here is a wooden skewer. You probably know this. You have an idea of how much it weighs since you've held one before. And here are pieces of balsa wood. There's about as much balsa here as at least 2 skewers in length, maybe even enough for 3. Although the scale now shows 0.1 grams, and for some reason the tare function isn't working properly right now, but let's see how much the skewer weighs. So this is about 0.8 grams. The total weight of the tiny model airplane was just about the same. It was exactly 1 single gram. So the whole thing weighs about as much, has about the same mass as one of these skewers. That's why the skewer is actually completely unsuitable for building this. Now I'll put some pieces of balsa wood on the scale. The skewer is unsuitable because the structure would be too heavy and would not take off. And even balsa wood seems to be right on the borderline of being too heavy. But this is so much lighter, about half the weight, and these pieces would make up at least the length of 3 skewers, so balsa wood is really, really light. Aluminum foil has almost no mass at all. Here's a little piece. I'll crumple it into a ball and put it on the scale too. So the smaller plane weighed about this much, which doesn't actually fly, but I'll show you what happens anyway. Here are 3 little towers made from balsa wood, 1, 2, 3, and there's a very thin copper wire stretched out here. I removed the insulation by heating it with a soldering iron and burning it off. I hope you can see it on camera. Maybe here you can see that this thin little copper wire is stretched out. The high voltage just jumped right across the 2 centimeter gap a little bit earlier than I expected, but even then it didn't lift off. I had a very interesting experience with this device. I didn't plan to build it this way. The way I originally designed it, it didn't work, but then by chance, it ended up becoming functional. Let me show you what happened. At first, I designed the whole thing so that I covered this box, this plastic pill box, with aluminum foil, just like you see here. This was the rotating part, so this part here is the rotor. And there are 4 blades. Here are 2, here's the third, and on the other side is the fourth, which I took from a utility knife. Each blade is basically cut into a rectangular shape, so I cut off this part here. There's no triangular section like the one in my hand here as well. I rounded off the corners here, 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 and here. And this part of the blade isn't actually the sharp edge, since the edge is here. I coated this with glue so that the corona discharge wouldn't go toward the air, like you saw earlier with the Tesla coil, but so that, if possible, the charges would move toward the rotating part. Right here, the gap is incredibly narrow, measuring about 3 millimeters between the box and the edge of the blade. It is the same here as well, here too, and right here as well. The whole structure stands on a tube from an effervescent tablet container, on this side and over here as well. I carefully sliced it right down the middle, and this is the plastic holder from a screw top box. There's one here and another one here. I placed a standard plain bearing component on both sides. Here's one of them, and trust me, the same thing is on the other side as well. What's also very important is that one blade is connected to the positive voltage and this one is connected to the negative voltage. And on the opposite side, this is also connected to the negative voltage and that one to the positive. So it goes plus, minus, alternating like that, meaning there is always a voltage difference between 2 neighboring blades. I expected that what would happen when this cylinder was inside is that the charges would move onto the surface of the aluminum foil, and just like in the cup experiment, it would turn and the other blade would neutralize it. So the positive one charges it and the negative blade neutralizes it. That's not what happened, and there's a simple reason for this. Obviously, I didn't break this cylinder anywhere, so there aren't any cutouts in it like in the cup experiment. And when I realized, oh, I forgot the cutouts, I started cutting the strips here. But I was so unlucky that the entire aluminum foil that was on this cylinder came off. When it came off, I thought, I'll try it without the aluminum foil, and it still works. I'm a bit surprised that it works even without the foil, but there's an explanation for this too. The charges will still go onto the surface of this medicine container, it will turn, and the negative pole will neutralize it. I am going to use this long rod to gently nudge the little cylinder into place so that it finally starts spinning on its own. Right now, I am turning on the power generator. Now that the generator is up and running, I'll give the cylinder another quick nudge, and as you can see, it works perfectly. Let me bring the camera in to show you everything up close. So, what you are looking at here is a real functioning rotary electrostatic motor. It just keeps spinning around and around, continuously moving just like that. This particular component functions exactly like the other one I demonstrated for you at the very beginning of this video. That is essentially how the whole mechanism works. Much like that first example, this one doesn't really have much torque to speak of either. Or to put it more precisely, its rotational torque output isn't very high at all. Because of that, it doesn't consume a lot of electrical current during operation. I suspect its total power consumption might be somewhere around 1 milliampere, but depending on the conditions, it could actually be as little as 100 microamperes, or even 10 microamperes. So basically nothing, because from that power supply, 20,000 volts comes out of this. If you multiply 20,000 by even 1 milliamp, that's significant power. So the current is likely much less than 1 milliamp.
In today's video, I've included little theory and told little history, but the devices speak for themselves. The great thing about the cup one is that it's very simple and easy to build. The ion thruster works surprisingly well. It was capable of a relatively high thrust. How you can make a motor out of a medicine or vitamin bottle like this is also brilliant. With a few blades, you can make an electrostatic motor. Unfortunately, this flying device didn't work. Anyway, if it had worked, it would have had to be tied down at its 3 points, its 3 legs, because otherwise when it takes off it's very unstable and tips over. And if you liked the video, then as usual, give it a like. Thank you very much. Bye everyone!